Hello, everybody. Today, I'd like to give an introduction to the paper Computing Persistent Homology by Afra, Zomorodian, and Gunnar Carlsson. I'm targeting this talk at graduate students, but I hope others find it as well. My goal is to give an introduction to the main ideas of this paper with the hope of inspiring you to check it out in more detail. This paper was published in 2004. Afra was a postdoc working with Gunnar at Stanford at the time. It's a follow-up paper to the paper by Afra Zomorodian and Herbert Edelsbrunner and David Letcher, which introduced the persistence algorithm for the first time. This paper, which we're talking about today, puts the persistence algorithm in a more mathematical framework. In particular, it explains why you can have any field of coefficients, not just Z mod 2Z coefficients. All right, so I'll give a brief introduction to persistent homology, although in this video, I'm hoping you've seen that before. I'll describe how there's an equivalence between persistence modules and F adjoint T modules, where F is a field. I'll describe the decomposition theorem, which takes any persistence module and breaks it up into bars. And then I'll describe some of the insights behind the computational algorithms discussed in this paper, although I'll be brief. And I'll also briefly mention some of the experiments they do in the paper. Okay, so you can apply persistent homology whenever you have an increasing sequence of spaces. Here we have a space at time 0, which includes into a space at time 1, which includes into a space at time 2, etc. And first we'll talk about the zero-dimensional persistent homology. So you'll see that at time 0, you have two connected components. Those two connected components correspond to these two bars at time 0. One of those connected components lives forever, okay? But the other connected component you'll see dies at time 1. Because the A and B get joined, right? A and B get joined, they get joined into the same connected component. Even though a connected component dies at time 1, a new connected component is introduced, which then dies at time 2 when it gets connected up. And then after time 2, we have just one connected component forevermore. Let's look at one-dimensional homology, drawn down below. There's no one-dimensional homology until we get this loop at time 2, corresponding to this bar, which lasts until that loop is finally filled in at the ending time. At time 3, a second loop appears, and the second loop dies at time 4. So the hole that appears at time 3 dies already by time 4. Okay, so mathematically what's going on here is we have an increasing sequence of spaces. K naught includes into K1, which includes into K2, which includes into K3, etc. And then you can apply homology with coefficients in a field F to get the following, okay? So I won't write the field F, although the field F is sort of important for what we do throughout. We have homology of the 0th space, homology of the first space, homology of the second space, etc. The inclusion maps between the spaces give you maps between the homology groups. They don't necessarily give you injections between the homology groups, just maps between the homology groups. Okay. So we have a sequence of vector spaces. Since we're taking homology in a field, each homology group is a vector space, and we have maps between the vector spaces. That's a persistence module. The thing drawn at the very bottom is a persistence module. And today we'll discuss how it breaks up into the intervals as drawn above. On the next slide, I will just call this my 0th vector space, my first vector space, my second vector space, etc. So we'll forget for a moment that these vector spaces were coming from homology groups of spaces, and we'll just consider arbitrary vector spaces equipped with linear maps between. So the diagram with the V's down below is a more general persistence module. Great. So this is the most technical slide. I want to explain an equivalence between persistence modules and graded F adjoint T modules. So I have my persistence module here. I have vector spaces V0 up through VF, V5, and these are all vector spaces over the field F. And I want to explain how you can think of this data of all the vector spaces and the linear maps between them as a graded F adjoint T module. Okay. So the elements of this module are just elements little v0, little v1, little v2, etc., where little v0 is an element of the vector space capital V0, etc. So this list of 6 elements is in the direct sum of the vector spaces from capital V0 up through capital V5. So that's the set, which is this capital F adjoint T module. Any F adjoint T module needs an action by F adjoint T. So pretend that 3 is an element in my field capital F. It doesn't need to be, but I'm just trying to introduce you to the ideas. How does 3 act on one of these elements, little v0 up through little v5? Well, it just acts on each element independently, right? V0 is an element in a vector space, capital V0, vector space over field F. And since 3 is an element of my field F, I can act on this element in the vector space. Okay, so 3x on this element by sending it to 3v0, 3v1, ... all the way up to 3v5. What's much more interesting is how T acts. Okay, so Afra and Gunnar had the nice insight to realize that because we don't have one vector space, but because we have maps between them, we can encode that map between vector spaces as using this variable T. So this variable T is going to map from one vector space to the next. Okay, maybe from vector space V0 to V1, or maybe from vector space V3 to V4. etc. So how does T act on this element? T acts on this element. So in the first entry, we always have 0, just because there's nothing mapping in to V0. Okay. But on the second entry, I'm going to map F0. I'm going to map V0 under F0 to get an element in my vector space V1. And to get an element in vector space V2, I take my element V1 and apply F1, etc. So where this ends is to get something in V5, I take the element V4 and apply my map F4. Okay, so T is shifting everything over. Shifting everything over by 1. Let me try to diagram it out here. So I have little v0, little v1, little v2, little v3, little v4, and little v5. And little v0 is in capital V0, etc. Acting by T does the following. It takes all of these elements and shifts them over. Let me try that again. It takes all of these elements and shifts them over. Okay, but you can't just shift them over directly as I drawn, because V0 is not an element of V1. V0 is not an element of V1, okay? the way I shift over is I use the maps that I have. So the way I shift over is by applying F0, by applying F1, by applying F2, by applying F3, and by applying F4. You'll notice that V5, element little v5, has been pushed off the page. We're not using it at all. And there's nothing good to push into the slot V0, so we just put a 0 there. Okay, so in red, up above, you can see I've really just drawn this, I've just drawn T acting on V0 up to V5 down here. All right. Now that you know how T acts, you can guess how T squared acts. T squared acts just by doing T twice, okay? So we apply T once. When we apply T again, we're shifting over 2 slots. So neither the V, capital V0 nor capital V1 have interesting elements in them. But an element that's in capital V2 is obtained by starting with V0, applying F0, and then applying F1. Okay, and an interesting element in V3 is obtained by starting at V1, applying F1, and then applying F2. And then at the very end, we'll have, in vector space V5, we'll have element V3 after applying F3 and then applying F4. All right, and this is really an F adjoin T module. You can act by an element 3 plus T squared, just by first acting by 3, then acting by T squared, and then adding them together. So I've already done each of those independently, and if I add them together, I'll get 3V0 in the first place, coming from 3. I'll have 3V1 in the second entry. And then in the third entry, I'll have 3V2 plus F1 applied to F0, applied to V0, etc. So this paper proves that these 2 categories are equivalent. The category of persistence modules and the category of graded F adjoin T modules. I haven't talked about the grading too much here, but we have 6 different slots in our grading given by these 6 different entries that any element is broken up into. Wonderful. Let's move on to the decomposition. Okay, so I want to explain mathematically why persistence modules break up into barcodes. I want to start with an analogy. Given a finitely generated abelian group, capital G, you can always write it as a direct summand of copies of the integers plus some number of direct summands of torsional parts. So Z mod NZ. And in such a decomposition, we call the copies of the integers the free parts, and the Z mod KZ parts are the torsion parts. Okay. There's an analogous theorem when you don't have an abelian group, but when you have an F adjoin T module, or any module over a PID. If F is a field, then F adjoin T is a PID. Again, you have a free part, just copies of our PID, which in this case is F adjoin T. I should say PID is principal ideal domain. If you haven't heard about it, not a problem. So you have a free part, which is just copies of our field adjoin T, and you have torsional parts, which, because we have a field, can always be written as F adjoin T mod some power of the variable T. And I'll describe this on the barcodes in a moment. You'll see how this modulo T to the power NJ appears. Okay. Persistence modules are in equivalence with finitely generated F adjoin T modules, where the change here is the grading. The grading gives these shifts, okay? So sigma here means shift over to the right by some amount, alpha I. And same thing, sigma here means shift over to the right by some amount, gamma j. What's really beautiful is that the free part corresponds to the finite bars in our persistence diagram. And the torsional part, the free part corresponds to the infinite bars. And the torsional part corresponds to the finite bars. Okay, so we're doing homology over field coefficients. So for any specific space, our homology is a vector space. There's no torsion. But what's beautiful here is that we have many different spaces being mapped to each other. And so the torsion part in this decomposition appears as the finite bars, which eventually die, right? That feels like torsion, something is dying. Whereas the free part in this decomposition corresponds to the infinite bars that never die. Beautiful observation by Gunnar and Afra. So let's return to our starting example. I want to show you how the birth and the death times of the bars really come out of this decomposition theorem. Okay, so we saw that for zero-dimensional homology, we had a connected component that started at time 0 and lasted forever. Okay, so that's an infinite bar, and its birth is given by alpha. So here, alpha 1 is equal to 0, because this bar is born at time 0. If alpha 1 were equal to 3, this infinite bar would instead start at time 3. So alpha 1, or the alpha i's encodes the birth times of my infinite bars. What else do we have? Remember, we had 2 finite bars. We had a finite bar like this, plus 1 more. So this finite bar has gamma 1 equal to 0. It also starts at time 0. It lasts for 1 step. So n sub 1 is equal to 1 because this bar has length 1. I'll describe that a little bit more once we get to one-dimensional homology. All right, we had 1 more finite bar in this zero-dimensional barcode, and it started at time gamma 2, which is equal to 1, and it also has length 1. So n2 is equal to 1. All right. Let me move to one-dimensional homology. Okay, so for one-dimensional homology, the first hole is born at time 2, and it's finite. It lasts up until time 5, but no longer than that. Okay, and so let's restart our indexing back at 1 again. So let me erase this. So now we're doing one-dimensional homology, totally different module. Gamma 1 is equal to 3, okay? Because this bar starts at time 3. And n sub 1 is equal to 3 because this bar lasts for 3 steps. So I want to tell you how to interpret this torsion, okay? Start with an element right here, okay, in our persistence module. Apply t once. Remember, applying t maps you forward in time, so you end up here. Apply t again, that maps you forward in time, so you end up here. And then apply t a 3rd time, okay? That ends you here, which is now 0. The bar is dead. The bar continues no further. So I've applied t 3 times, okay? And I've gotten to 0. these intervals are all half open. So it's, this interval here is a half open. So when I apply t 3 times, I reach the end of my bar, you know, I'm to 0. I've been killed off. Just like here, when I'm mod out by t cubed, that means that if I apply t 3 times in this module, I have the 0 element. Okay, and then in one-dimensional homology, we have one more bar. It starts at time 4. Sorry, it starts at time, oh my goodness, I had my times wrong. Okay, this bar started at time 2. Anyways, the other bar in one-dimensional homology starts at time 3, and it has length 1. Okay, so that's given you a little bit of intuition about how the decomposition exactly determines the barcodes. When you're computing persistent barcodes, you're computing this mathematical decomposition and vice versa. Wonderful. So I'm almost done. I just want to touch on some computational elements. I'm not going into the details. I just want to tell you what's in this paper. So this paper shows how you can think of the persistence algorithm as Gaussian elimination. But now the elements in your matrices aren't just, say, in your field. They're in your field adjoined T. So here's a boundary matrix. This is the one-dimensional boundary matrix going from edges to vertices. So you can see that BC has as its vertices in the boundary, it has vertex C and vertex B in its boundary. BC doesn't have A or D in its boundary, and that's why those elements are 0. Okay, you have T's in these matrices when the elements are not at the same time. So BC appears at the same time that edge, vertex C appears, right? BC appears at this step at the same time that vertex C appeared. So that's why this element is 1, because BC and C appeared at the same time. By contrast, BC appeared one step later than vertex B, right? Vertex B began at time 0, edge BC begins at time 1. So since they're off by 1 time, that's why you have a T in this matrix. All right, you do standard Gaussian elimination. It turns out that you can do that over a principal ideal domain. And you get it down into this reduced form. The pivots are drawn in boxes. And from this reduced form, you can count the dimensions of the one-dimensional cycles, okay? So the one-dimensional cycles have dimension 2. They write out what those cycles are. So this is the cycle that corresponds to the square. And Z2 is the cycle that corresponds to this triangle, okay? As you see down here. So by reducing these boundary matrices, you can find your cycle space, your one-dimensional cycle space. You can also find your zero-dimensional boundary space. And so when you do not only this boundary matrix that takes you from edges to vertices, but when you also do the boundary matrix that takes you from 2 simplices to edges, then you can use the cycle space for one-dimensional cycles and mod it out by the one-dimensional boundaries to get one-dimensional homology. It's really nice that they cast this all as matrix operations because we're used to seeing matrix algorithms, and it's in a format that's easily interpretable by humans. However, they also describe how to do these computations in a much more sparse or computationally efficient manner. The point is that the boundary of an edge is always exactly 2 vertices, right? And similarly, the boundary of a triangle is always exactly 3 edges, and the boundary of a tetrahedron is always exactly 4 triangles. So these boundary matrices are sparse. So there's really no need to store the entire matrix. Many of the entries are 0. And this paper describes a sparse data structure storage, which leads to a very fast algorithm. This paper mentions some experiments that they've run. So these data sets, capital K corresponds to a Klein bottle. The meshing of the Klein bottle is drawn on your screen. Capital E corresponds to a data set that measures electrostatic charge. And capital J is quite interesting. It's a data set of jet engine flow, so the turbulent airflow out of a jet engine. They tell you the number of simplices in the final simplicial complex that you build. They tell you how many steps they have in their filtration. They tell you how long it takes to compute the filtration, I believe. And then they also tell you how long it takes to compute persistent homology. And computing persistent homology often doesn't take very long at all. So, for this Klein bottle, I think it takes less than 0.01 seconds to compute the persistent homology. All right, so I hope I've whet your appetite and given you some intuition behind this paper so that you're now prepared to go off and study and learn all the details. Thanks.